Okay, so welcome to this week's Origins Colloquium by Professor Tomonori Tatani. Tomo, as I know him, received his PhD in 1998 from University of Tokyo and spent a little bit of time at NAOJ and also at Princeton, where I met Tomo then in those years. Then he became an assistant professor in 2003 at University of Kyoto University. Then associate professor there after a few years, and then was it 2013 you moved to University of Tokyo as a full professor.
Yes.
And Tomo has worked on a whole range of topics, lots to do in cosmology and dark matter and gamma ray bursts through the universe. But also more recently, I see you've been working on a new topic, the origin of life. So
Yeah.
maybe at some point we'll have you back to talk about that.
Yeah.
So today you're going to tell us about this very exciting result about potential signature for dark matter annihilation. So welcome, Tomo.
Okay. Thank you very much. So it's nice to meet you to everybody. So I'm Tomo Totani, and so today I'd like to talk my very recent study about dark matter annihilation gamma ray search toward the Milky Way halo. And I believe that I found some very interesting signal, excess signal, that can be possibly dark matter around 20 GeV. The paper has been submitted to you can find on the arXiv, and the paper has been submitted to the JCAP, and I already got a positive referee report, and I already submitted a revised version a while ago. So I expect the paper will be accepted soon. And in the chat, I put the URL for the PDF of the slide of today's talk. So if you like, please download it and for your convenience. Okay. So let me introduce about myself. Actually, I'm a theoretical astrophysicist working on mostly like transient or high energy astrophysics like supernovae, gamma ray burst, fast radial burst recently, and also galaxy formation, cosmology. Actually, I'm just a theorist, and in fact, I had no experience about Fermi data analysis before this work. So maybe you may wonder why such a person started the search for the dark matter gamma rays using Fermi data. So I will talk about that. But anyways, I must thank Tsunefumi Mizuno. He's a member of Fermi Large collaboration, and he gave a lot of general advice to me about analysis and about the treatment of the Fermi data. So I really thank him. But anyway, so then now let me explain why I somehow started this project. Actually, my group has been working for many years about the theoretical modeling of the gamma ray background, the extragalactic gamma ray background in the GeV region, mostly observed by Fermi. And this is my recent work with my student Junlin Chan, and he made I believe currently the best most reliable model for the gamma rays background from the star-forming galaxies. I mean, star-forming galaxies produce cosmic rays, and they interact with interstellar mediums to produce gamma rays. And then when we compare the model to the data, actually we found that around 1 GeV region, these star-forming galaxies have a quite large substantial contribution compared to the Fermi data, but somehow they rapidly disappear beyond 10 GeV. And this decline is actually a very robust prediction because this is the intergalactic absorption of the gamma rays. That is, gamma ray interact with optical and infrared, near-infrared background radiation, so they produce E plus minus pairs. So this absorption is a kind of robust prediction if the fundamental physics theory is correct. So the question, I just wonder what is this kind of bump excess? And because to explain this, you need some kind of very extreme spectrum, because in this lower energy regions, there is not so much room for, because there are so many other contributions by other sources. So somehow, I just wonder maybe the dark matter annihilation signal is something like this kind of very unlike not power law, but peaking at some energy. So this kind of a kind of strange shape, spectral shape, may be useful to explain these parts. So maybe I just wonder maybe something weird is happening. Maybe dark matter is appearing here. And if this speculation is correct, the dark matter annihilation signal that is also known for many years. That is so if the dark matter annihilation is contributing to the extragalactic background, then theoretically we also expect a comparable contribution also from the Milky Way halo. So the Milky Way halo contribution should also be visible. Then my step of consideration is thinking is okay, in that case, then maybe there may be some excess of kind of gamma rays in this energy region around toward the galactic center or galactic halo. So this is actually the original motivation I decided to look into the Fermi data. Okay, so first here. So let me briefly introduce the general introduction, but maybe some of you are already know well. But okay, so the WIMPs, weakly interacting dark matter particles, is a very strong candidate for the dark matter. It's typically becomes the mass range around the GeV to TeV, that is so-called electroweak energy scale. And in the case that we expect that some relic particles of this from the early universe, and the relic abundance in the universe now is determined by the annihilation in the very early universe. So actually, the annihilation cross section of the WIMPs is related to the relic abundance now. So this is the kind of a time evolution of the. So it's basically if annihilation cross section is larger, then relic abundance goes down. So to explain to match the observed dark matter density now, then it is just very simple result you get is in the simple case you can predict the annihilation signal annihilation cross section should be something like this standard relic cross section. And what is interesting is theoretically from particle physics, this cross section is very close to the weak interaction cross section expected for the WIMPs from the particle physics theory. This is so-called the WIMP miracle. So, in fact, there are so many well-motivated theoretical candidates like supersymmetry theory. So this is why the WIMP is one of the most popular dark matter candidates, maybe perhaps the single most popular dark matter candidate. But anyway, so there are so many studies. And also very interestingly, so such WIMPs can be searched by observationally in many ways. So one is a direct detection by the underground experiments. And another is an indirect detection that is relevant to my work. That is simply observing the annihilation gamma rays or neutrinos from the sky, like the galactic center. And also finally, as also particle accelerator experiment can probe this possibility. So there are so many studies for many years. But somehow, so far, we have not yet detected any convincing signal. Now, so in this work, I consider the gamma rays from annihilation gamma rays from WIMPs. So if it's the simplest observationally, if the WIMP two WIMPs annihilate into the two-photon state, then we expect a monoenergetic line gamma rays, and in that case, very sharp line gamma rays are very easy to detect. But unfortunately, this branching ratio to this two-photon production is rather theoretically most theory predict it should be very small. It is prohibited, so it's very uncertain. The more theoretically expected scenario at annihilation channel is kind of decay, annihilate, and produce other standard model particle pairs. Like the most popular case is B and anti-B, and also BB bar or W plus minus. And then after these are produced, these are produce a cascade of many particles. And then finally, they produce kind of not line, but continue gamma rays like this. The spectral peak typically about 10% of the WIMP mass. And that's the most important reason. This is not still it's continuous, but it's not like power law. So it's unlike many power law spectrum from the many astrophysical sources. So it is this non-power law spectrum is can be a signature of the dark matter. And in this case, this branching ratio to this annihilation channel can be of order unity. So we expect this is a kind of mainstream annihilation channel. And then you saw somehow maybe this is some I'm sorry, but I'm not sure. But it's gamma ray flux, and expected from the summer relic cross section is close to the sensitivity of the gamma ray telescope. So so many observers have searched the gamma ray signal from galactic center or so nearby galaxies, but not yet. Of course, it's not yet found. And so this work, I concentrate on the Milky Way halo. It's a halo region. So not to disk, and not excluding disk or excluding galactic center, but rather I search the more diffuse region in the halo region. And so in the past, of course, some people already made a search for annihilation gamma rays in this halo region. The most important is officially Fermi Large teams has published official paper about this. But actually, this is a rather old. The paper is 2012, and they use only the 2-year data, the first 2 years of the Fermi Large data. And somehow after that, Fermi Large data collaboration did not publish any paper about this halo region. And not only Fermi team, but also actually there are not so many papers on the halo region compared with other region like galactic center or dwarf galaxies. I guess some possible reasons is so one is there is a so-called GeV Galactic Center excess is known that is peaking at around 2 GeV, and this excess can be dark matter annihilation. Many people pointed out this possibility. And in that case, the energy dark matter density profile is a bit steeper than NFW, the standard NFW model. But for this GCXS, another strong candidate is astrophysical explanation is millisecond pulses. So currently it's so much debate, and you cannot decide which is better. So many people say that currently dark matter and the millisecond pulsars are almost equally good description of the excess. And another reason why people don't make such in the halo region is there's some diffuse astrophysical structures are known in the halo region, like loop 1 and also famous Fermi bubbles are found. And obviously these are kind of a noise or obstacle to search dark matter gamma rays in this diffuse extended region. But probably these for these reasons there is not so much halo region search for dark matter. So I decided to do that. And so I use the latest data. It's actually this is a 15 years Fermi Large data. So this is almost 7.5 times larger data set than the data used by the Fermi Large team. So I will consider these diffuse known astrophysical emission, and then I examined the existence of the halo component or not. So this is my work. So this here is some details about Fermi data analysis. So this is maybe if you are not Fermi expert, maybe these are a bit too much technical. But I use this kind of Fermi data properties, and simply I set the region of interest is the galactic halo. So we set in the Cartesian coordinates and galactic latitude and longitude within the plus minus 60 degree. And also I exclude the disk region, to within 10 degree in the galactic latitude, because you can see obviously in this region there are so much strong emission, gamma ray emission by mostly cosmic ray interaction with interstellar gas. So these are very noisy. So I removed this. And then from this data, you can compare the theoretical model to the data by likelihood analysis. But here, because the dark matter annihilation signal is very rather smooth in the Haro scale, so I calculated the likelihood as for the photon count for each cells of 10 degree times 10 degrees. So this size, because Haro is extending smoothly. And actually, this is a bit, in many studies about Fermi data analysis, including the Fermi public tool, is that they calculate the pixel scale calculation of the likelihood. And but in that case, compared that, of course, we can save much computing time for the MC fitting. And also, another possible advantage of my approach is coarse-grained approach is, if you use a model of such as gas emission from the interstellar gas, there's a sort of fine structure, a pixel scale. But of course, model and data sometimes there's a mismatch and for the fine pixel scale. But if you use a coarse-grained likelihood, maybe this kind of mismatch does not affect so much for the likelihood analysis. So in this study I calculate the rather likelihood by coarse-grained grid.
Tomo, can I ask one quick question? So the spectrum of gamma rays from the cosmic ray interaction with the ISM, can you remind me what energy spectrum that is expected to have?
Mostly they power. So maybe this is a bit. This is like these are showing many spectrum of many components. For example, this is emission from interstellar gas, and this green is this is from inverse Compton scattering of cosmic electrons. But generally, these are mostly power law.
Okay.
So very different from the dark matter. But anyway, I will come back to this plot. Okay. Okay. Now, so we need to some model to describe data. Because I follow the many standard. I follow the standard approach taken by the Fermi Large team. First, there's known sources. There's known sources for the point sources. There is a Fermi point source catalog. So I use this to subtract the flux from the point source. And there are some extended sources like LMC or something. And these numbers are not so many. So I masked the region of the extended sources. And for the diffuse emission, the most strong emission is, as I said, the diffuse emission by cosmic ray interactions. And I use this for the GALPROP model. This is a very standard model in the gamma ray astronomy community for the very fine, sophisticated model for the galactic cosmic ray interaction propagation. And simply this model gives gas and inverse Compton scattering spectrum. So this is gas emission, and from this is inverse Compton electron emission. And I use this template from the model. And so loop one is quite known for many years for the radial diffuse structure. And as for this, again, so I follow the LAT team approach. That is, there is so-called geometric model. That is simply they assume geometric shell of uniform emissivity. And they assume two emission shells. They suppose this is a nearby supernova remnant. And then as these two shells you can calculate a map. And so I use this template for the loop one. This is the standard approach taken by Fermi Large team. And also there is an isotropic background that is extragalactic. We know that there is extragalactic background. And for the dark matter halo, I used I simply assumed that NFW profile for the Milky Way, and the parameters are from the Via Lac 2 simulation for the Milky Way size galaxy. And this is also popular use in this kind of dark matter search. But also you need to assume some emissivity of gamma rays. And so here I use 3 models. One is the NFW rho squared. So for this, this is simply the emissivity proportional to rho squared. This is a case of a standard annihilation with a smooth density profile. And I also test the NFW rho linear. This is a case that if within the dark matter halo, in cold dark matter scenarios, there may be some very substructure and subhalo. And if in such a case, maybe if subhalo number density is proportional to the dark matter smooth mass, then maybe we expect this simple proportional relation. And also another possibility is that if dark matter does not annihilate, but simply if dark matter decay, once one particle decay, then of course we expect this dependence. Another model is NFW rho to 2.5. I use this as a model of the GC galactic center excess, because as I said, for this galactic center excess, previous studies suggest that the density profile in the inner region is something like this. And if I assume this emissivity with this normal NFW, then I got the same gamma ray profile in the central region. So I use this as a model of the GC excess. And also finally, also I need to model the Fermi bubble template. And for the Fermi bubbles, there is not so useful analytical template. So I use by myself following the similar approach for the Fermi Large papers. So this first, I simply start from the flat Fermi bubble template with a typical shape of known Fermi bubble, and fit with the observed map by using the flat Fermi bubble template and GCXS. And the fit to the map is done independently for each energy bin. And by MC fitting, you get the best fit for each model, for the various model components. So this is the result. And actually, this kind of a fitting is also mostly similar to the Fermi Large papers. You can see also, the region is a bit different, so not exactly the same, but for the many components, I got similar spectral shapes to the Fermi Large papers. So I'm mostly confident with this result. And then by this fitting, I get the Fermi bubble image. That is, by this fitting, I got Fermi bubble, flat Fermi bubble template fit. And so also there is fit residual. So the flat FE template plus residual is image of the Fermi bubbles. So I take 4.3 GeV energy bin. This is typical for Fermi bubbles. And if you see this, of course, you can see clearly Fermi bubbles for the positive flux in the red. But also somehow there is some strongly negative region in blue. And this blue region is actually corresponding to the gas map of the GALPROP. So this is most likely coming from the some model uncertainty or model mismatch of the gas of GALPROP. So from this point, because my purpose is to search for dark matter halo-like excess, so I take this approach. So I add this red positive flux map, this is red, and negative flux red map. These are separately included as fitting templates. And here I made this at the 4.3 GeV. So I use this template as energy independent template for all energy bins in the following fit. So by this treatment, so of course because I included the residual map in the fitting template. So at 4.3 GeV, of course we can fit the data without any additional component. But dark matter spectrum is very strange shape, And if there is a halo-like excess with a strong energy dependence, then by this fitting in other energy beams, we expect some excess of halo-like component that can be positive or negative. So this is the approach I take to search for the dark matter component. And this is the result for the fit, including so this plot is the same as the same slide as previous slides. And this is the light one is a fit excluding disk. So this previous fit is including a galactic disk also, and then you can see this is a galactic center excess, including galactic center excess model. This galactic center excess is similar to the previous studies. But what is interesting is if we exclude the disk region, we fit only halo region, then here, so 4.3 GeV, it is the same because as it should be, because I use the residual map of this energy beam, so fit results should not change. But if you go to the high energy range, high energy beams, the behavior very different. Yes, if you simply exclude disk, if you see only the halo, then in around 20 GeV, I got very much larger excess of halo component. So this indicates that is around 20 GeV, there is some halo like component, and of course this is not this is suppressed when we include the disk. So this suggests the much not less concentrated, but shallower profile than galactic center excess. Such a halo component is existing in around 20 GeV. And so I tested instead of GC excess, but I tested this low square and low linear. That is shallower halo profile. And then again, so this again by this fit, anyway, also I again found some peak around 20 GeV. So this again confirms that some halo like excess exists in around 20 GeV. And this are plot in log scale, but here I plot a linear scale in the y-axis for the three models of the halo model. Then you can see so in all case this halo excess sharply goes up from 1 GeV to 20 GeV, and then rapidly goes down. So this is something like very strange spectrum, maybe dark matter. And also there's some negative data point maybe because we introduce a residual map template around the energy beam here. So maybe this makes the halo component is reduced around here. So maybe this negative data point, negative result maybe by some halo component may be absorbed by the residual map template. And anyways, also we can also check the likelihood among these three models. And so this tip is because some models can be fitted at zero flux at this energy beam. But simply if we see that 20 GeV peak, so there are some likelihood is difference can be seen. Actually, we found that the NFW low square is the most favored, best match. It's better than NFW GC excess by more than about 2 sigma, and actually much better than NFW low linear. And here's the radial angular radial profile. Here at 20 to 20 GeV, that's most signal is the strongest. And here's a data point, and here this curve is dark matter halo model, best fit dark matter halo model, and the data point is best fit model plus fit residual. And you see for the three different halo models, the data points are different. This indicates that the fit is more a bit degenerate with some other model component, and that is actually the isotropic background flux. because if you go to the halo, if you go to the tail region of the halo component, it is it's difficult to discriminate from the isotropic background. So you can imagine that is some tail of halo emission is a bit degenerate to the isotropic component. But actually, when I checked this is a level of the isotropic background reported by Fermi Large papers. So this is the level of the extragalactic background, gamma ray background. Now I found that for the NFW rho square case, the isotropic component is actually nicely consistent with the isotropic background flux measurement by Fermi Large. But on the other hand, if we choose NFW low linear, then in this case, a very shallow profile. And in this case, the tail region is actually, if you even go to tail region, the flux is higher than the reported extragalactic background. So this indicates, in the case of the NFW low linear case, we can fit the data, but in this case, there is no room for the extragalactic background. But of course, we know that there should be extragalactic background from many sources. So this certainly indicates that NFW low linear is the fit looks good, but actually, if you consider the isotropic background level, NFW low linear is certainly consistent. Is not consistent with the data. And also another point is if you go to the extrapolate to the galactic center. So I said among the three models, NFW low square is the best fit. But if you go to the galactic center, so this is galactic center excess fit, including the galactic centers or galactic disk. So if this red curve is a factor of 4 over prediction, this indicates that maybe the NFW low square model is maybe overproducing the galactic center flux. So this implies maybe around, especially in the galactic center, so this halo-like excess profile is maybe shallower than the NFW profile. Anyway, this is a bit details discussion. Okay, so now let me check the morphology of the map morphology. So here is a 21G energy bin. The halo is the strongest, and here, so this is a fit. This is a fit residual of the fit, but but without including any halo component. So because halo component is not included in the model, so the fit try to minimize any halo-like component, but still the residual, you can clearly see the halo-like residual here. And this is the fit including the NFW low square model. And here I'm showing the best fit NFW low square model plus residual. So this kind of image of the dark halo-like excess. And in this case, halo-like excess can be more clearly seen. And actually, this is a best fit halo model. So these are simply very similar. And finally, this is simply fit residual for the fit including this halo model. So if now you can see the so by this NFW low square fit, the final fit residual is basically almost you don't see a strong residual anymore in all the region of interest. So I say this means that the fit is successful overall. I mean I fit the data with the known components plus halo model. Then this is a good description within the region of the interest. Now here, the morphology of this is for 21 GeV. That is a halo best fit halo plus residual. And then I check the in other energy band. Then I confirm the trend that is of the energy spectrum I showed. That is at the lowest energy bin is negative, but if you go to the higher energy bins, you can see clearly the halo-like excess can be evident. And beyond the 20 GeV, the 35 GeV, this halo can be seen. But if you go to the higher energy range, then the halo signal disappear. So this again, this confirms the energy spectrum, and also the overall this morphology of the halo excess is consistent with a kind of isotropic halo-like signal. Now, so 30 minutes has passed. So maybe this slide is a bit kind of technical, but so anyways, I examined many systematics. Like I split into the four quadrants around the GC, and also I changed some treatment about Fermi bubble template modeling, and also I test some other background model. That is, I use also LAT GIEM. This is official map recommended by LAT team for the general point source analysis. But in this background model, this includes a non-template patch that is adjusted to fit residuals. So that purpose is to erase any diffuse structure like Fermi bubble or galaxy center excess loop one. Because these diffuse structure is not so good for the point source analysis. Anyway, so this kind of map is try to minimize any diffuse structure. So you may expect the halo component can also be erased. But actually, still you expect that halo excess may remain because this patch is they assume some power spectrum above 3 GeV. But of course, so the 20 GeV halo excess cannot be described by a single power law. So still, I thought that okay, so there should be a halo excess may be still visible even against this LAT background model. And I see, in fact, also in this case, this green point, I still see the with 20 GeV excess with a similar spectrum. So this test is, I think, this good test. I mean. The halo excess is not much dependent on the modeling of the map templates. Okay, and so now finally, as I go to the dark matter interpretation, so I fit the halo excess spectrum with annihilation gamma ray spectrum. So there is a so-called PPC4 package that is publicly available, open package that is you can calculate the energy spectrum of gamma ray energy spectrum from assumed annihilation channel. And so here I took the 3 cases for the NFW low square, and 1 case from the NFW low linear. And for these because the baseline model of NFW low square this is negative, so this negative point is rather unphysical, and it is not. If you fit to this, you get rather strange spectrum. So I took some alternative fit, and this is more or less no minimum. The flux at the lowest energy is not strongly negative. But anyway, so these so for this spectrum, roughly, so the data point are consistent with the expected annihilation gamma ray spectrum used for the popular channel, that's a BB or W plus minus. And actually, according to the particle physicist, I'm not an expert, but according to particle physicist, the BB and the W plus minus is a very representative case, or theoretically expected. And also tau plus minus is also often considered. It's a leptonic case. But in the case of tau plus minus channel, the energy spectrum is maybe a bit narrower than the observed. So anyway, but the BB and W plus minus spectrum is in good agreement with the data. And you can derive the WIMP mass parameter by this fit. I got best fit is roughly the WIMP mass is about 0.5 TeV, and the annihilation cross section is this value. Now, so let's discuss about these WIMP parameters. So first, so let's compare this cross section to the previous constraint. Actually, the previous so for currently is most strongest upper limit for the annihilation cross section is reported by the dwarf spheroidal galaxy analysis. Actually, the value for the 20 GeV halo excess is coming here, it's mass and cross section. And this is with the intention with that is about a factor of 2 or 3 higher than the upper bound by the dwarf galaxy constraint observation. So this means that there is some tension between the constraint by dwarf galaxies and cross WIMP parameters inferred by my work. But actually, it's a tension, but not very, not the immediate discrepancy, because there is a large uncertainty, especially in the Milky Way. Halo dark matter density is rather uncertain because of both one the density profile function like NFW or other profile function can be possible, and also the normalization is normally made by the density around the solar system, and it is also uncertain by a factor of 2 or 3. Of course, also some uncertainty exists in the dwarf spheroidal galaxy analysis. So in fact, there's the famous GeV excess is the WIMP parameter for this is also in the similar tension with the dwarf galaxy constraint. But because of these uncertainties, generally people do not think that the GeV people think that the DM interpretation for GC excess is not excluded. But this is just a tension and not excluded. So I mean, still the dark matter, so this means dark matter interpretation for this 20 GeV halo excess is possible. And if you compare it with the theoretical expectation, as I said, the simplest case is a standard thermal relic cross section expected is this line that is corresponding to the observed dark matter density. And it is the cross section inferred from this halo excess is more than 10 times larger than this cross section. But again, of course, this thermal relic cross section is the simplest case, and of course, again, there are many possibilities of some enhancement of actual cross section compared with this simple thermal relic. So it is possible, and also again, so also another point is the Milky Way dark matter density profile there is a large uncertainty. So again, I think this factor of 10 difference is not much. Is not a serious problem. Okay, now so let me say something about the future. Okay, but of course, so my first conclusion is that this result, the 20 GeV halo excess, is consistent with dark matter annihilation. But of course, it is not yet definitive proof. So the question is how in the future how we should examine this indication. And future verification. So one good prospect for future verification is again the dwarf galaxy observation. So as I said, there is already tension between the dwarf galaxy observation and the halo excess. So modest improvement in the near future should lead to the detection from the dwarf galaxy with the dwarf galaxies with the same energy spectrum as the halo excess. So if the same with the same energy spectrum peaking at 20 GeV is observed from the dwarf galaxy and also galactic halo, I think this can be a very, very strong case indicating the dark matter annihilation rather than the astrophysical sources. And actually, in this regard, there is very interesting indication. Actually, there are already some papers reported. There is some excess of Fermi gamma rays from some dwarf galaxies. The most famous one is Reticulum 2. Actually, there are several papers, several independent groups report that there is some excess from Reticulum 2. This is, but statistical significance is less than 3 sigma. So normally they don't claim firm detection, but there indicates some excess exists. And by this latest paper, they derive the WIMP mass from the Reticulum 2, and also another is a William 1. So these dark matter mass is about a few hundred 500 GeV. So by this latest paper, the WIMP mass inferred from Reticulum 2 is very nicely consistent with the WIMP mass estimate inferred from my analysis of halo excess. So this is very, very interesting indication. My hope is so maybe 5 or 10 years more observation of the Fermi may lead to the found detection of the reticulum-2 with the same energy spectrum peaking 20 GeV. That is very, very interesting direction.
Hmm. So maybe
And another,
can you finish in about 1 or 2 minutes, Tomo?
okay.
Yeah.
And okay, so that's another line and gamma and neutrinos and some other possibilities like line gammas and neutrinos observation. But anyway, so okay, so this is so my last slide is just summarizing my conclusions. Okay, so okay, now I think I can take questions.
Great. Thank you very much. That was great.
Thank
Very
you.
exciting results. So we have time, yeah, we have time 15 minutes or so for questions and discussion. So raise your hands in Zoom if you would like to ask a question. I have lots, so not seeing anybody else, let me start. Can you motivated this from the overall excess of the trying to explain the extragalactic signal
Yeah,
as
yeah.
well. So maybe we can
Mhm.
just go back there. So the star-forming galaxies were anyway
Mhm.
low,
Mhm.
but it's more this high energy excess. So do you
Mhm.
think then, what is your conclusion in this regard here? Does
Okay. Yeah, okay. But certainly, so this is the kind of motivation that triggered my study about galactic halo. But if I'm not, but now Laz, I don't have a strong opinion of whether this bump can be explained by dark matter annihilation. But one reason is that I need more kind of careful modeling. I mean, because this plot is showing only star-forming galaxies.
Mhm.
But for the background, for the gamma ray background, there are many other sources are contributing, like blazars is also contributing, or many species of AGNs are also expected to
Mhm.
be
But
contributing.
I thought things that are at high redshifts or very distant objects wouldn't contribute at high energies because of.
Yeah, yeah. But the other point is some paper is producing nearby very hard spectrum blazars. Kind of some class of the blazars is a very hard spectrum, and and also they have low luminosity. So low luminosity means their redshift is relatively close.
Uh-huh.
If such a population exists, maybe it's contribution to this.
Mhm.
So yeah, so I think so. I think so. I think this is the initial motivation for me. I think it is possible that this for dark matter annihilation is also responsible for this bump.
Well, you have a
Yeah,
prediction. Your Halo model will make a contribution here.
yeah,
It's just a question
yeah.
of how much it is. Yeah.
Yeah, but another complication is for the galactic for the X galactic halo. I think the emission from the total halo, and in that case, substructure the degree of substructure can change the boost factor of the gamma ray luminosity from total halo. So
Yeah.
this is a bit rather uncertain. But also, it can change for the substructure is maybe more surviving in the outer region of the halo.
Mhm.
So.
Okay.
But yeah, the signal for the Milky Way halo is more central region.
Yeah.
In that case, so
Well, we'll come to the
maybe
central region in a moment, but Yanbo has a question next.
yeah.
You're muted, Yanbo.
Oh,
I
yes.
can hear you. Yes, I can hear
Oh,
you
okay.
now.
Yeah, can you
Yes,
hear me?
Yeah.
yes, please.
Oh, okay.
Yes, please.
So, you mentioned there could be a millisecond pulsar
Mhm.
signals as well. Do you imagine is there like other high energy sources which can also be like a confounding reason for your gamma ray boost?
Okay. Okay. So yes. So millisecond pulsar is for this. Millisecond pulsar has been proposed to explain this GeV excess in the galactic center. This is peaking around 2 GeV. So probably this is different from the halo excess I found. And for the millisecond pulsars, they say they're also peaking at this energy range. And so the millisecond pulsar can be explanation for this DC excess, but for the halo excess, is energy scale is 10 times larger. So maybe the millisecond pulsar may not be difficult to explain. On the other hand, of course, there are still some other possibilities. For example, for the GC excess, there are many proposals like some cosmic ray anomalous or some cosmic ray production near the galactic center. If you produce, but maybe in that case, of course the difficulty is you need to explain non-power law and the peak. So this is generally not so easy. If you produce cosmic rays, generates power law, but still, but of course, in principle, you can produce some, if you assume some cosmic ray production in the galactic center, and if you assume some assumption, maybe some ad hoc assumption about the cosmic ray production, and then sometimes maybe you can fit to this energy spectrum. And in this case, if you make such a kind of a flexible astrophysical model, maybe you can explain also for the Halo excess I found by my work. But in that case, the question is how natural is it? And so of course this is rather difficult, but this can be judged. It is difficult to judge simply. But I think this probably maybe for the future study. I mean, probably many people, maybe some people try to explain my Halo signal by some astrophysical process. And the question is how natural is it? So I think this may be a good trial. So let's.
Well, let me come to in the galactic center. Your model, or the model of annihilation, should make quite a strong signal at 20 GeV. So, is there any evidence for 20 GeV excess in the galactic center?
Okay, so this is here that is so this green is the fit of GCXS model, including the galactic center. So probably the galactic center, on the other hand, the NFW low square model in the Halo, if I extrapolate this to the galactic center, so it's a factor of about 3 or 4 overproduction. So this indicates that the NFW, the simple NFW low square profile is
Right.
It's not consistent with the galactic center. So one possibility is
right.
gamma ray profile can be maybe a bit shallower than this.
Right. No, that I understand, but shouldn't there still be some peak at 20 GeV in the galactic center? And I'm just wondering if there is any evidence for that. Or are you saying it's too is it too merged in with the 2 GeV excess that you cannot distinguish the peak?
Okay, so yes, in the case of this, if you assume the GCXS model, then around 20 GeV, there is some non-zero detection of the peak. So there is some peak centrally peak flux also in 20 GeV, but this is but simply if you include some simply, so this model, this simply assumes this very GCXS profile. That's kind of a more kind of a steeper profile. So I guess simply my so my thought is okay. Simply this model probably if you assume this NFW low square model and a bit shallower in the central region, then if you make a bit maybe factor of 3 lower flux in the galactic center, and then such a of course such a peak, there is such a peak is consistent with data point over here, because this is simply in 20 GeV. If you include the galactic this level with this Halo model is indicated for probably this fits the galactic center.
Well, but there's a data point there, but there's no, if anything, there's a minimum at 20 GeV rather than wouldn't you expect a peak in the spectrum at the galactic center? So
peak of, you mean morphological peak or
just
spectral peak?
In the energy spectrum, yeah, spectral peak at 20 GeV.
Okay. I think for that question, I need to do some another additional analysis because for this NFW low square fit, I fit only excluding this region. simply I wanted to avoid the galactic disk region because because there is so strong astrophysical
Well,
flux.
I
So
know,
yeah,
but astrophysical sources, as you mentioned, are generally power laws. So
yeah.
one should be looking for this 20 GeV.
Yeah, okay, yes, yeah, I agree. So it's simply I have not yet done. So it is interesting to see
Mhm.
to okay. So simply question is okay. So simply to again for including the galactic disk region, or maybe it's just I pick up the galactic center region and I fit this kind of NFW rho square Halo model. Then I can answer to your question. But I'm sorry, but I have not yet done.
No problem. Uh, Great. Any other questions? I still have more. So obviously the dwarf galaxies are very interesting. So you mentioned reticulum too. So
Mhm,
probably the next thing is just to stack several
mhm,
nearby dwarf galaxies.
mhm.
So is that something on your list of things to do? Or...
Yeah, but I think all this stacking of all dwarf galaxies are already done by some recent papers analyzing the dwarf galaxies in
Mhm.
search for dark matter annihilation. So probably, I think there are already so many papers by experts about the
Right.
dwarf galaxy dark matter search. So probably maybe there is not so much things that I can do. So
Well, but you mentioned even in reticulum too, there's a hint of 2 or 3 sigma,
yeah,
so presumably
yeah,
it would pop out.
yeah.
Um, okay.
Can you see some? I think this is probably the latest paper about the galaxy observation, and they say that there is tantalizing evidence for some from some dwarf galaxies. They say that okay, so it is important to continue Fermi observations, and then maybe another 10 years observation of Fermi will certainly they will result in the farm detection or not. So that is bit claimed by these papers. Yeah.
Mhm.
So,
Okay. Let's come to this. If the signal is real as a WIMP annihilation signal, you mentioned the rate coefficient is about 20 times higher than the relic, the thermal relic. So
mhm,
perhaps you could just expand a little bit on that to point. If
mhm,
I did want a thermal relic, a cross section,
mhm.
can I do it, or how, how would I do it?
You mean how to make
Yeah.
this consistent with summer rate?
Yeah, I'd have to lower my dark matter density that you're assuming, I guess.
Okay. I guess one
Oh.
possibility. Also, one possibility is okay. So depending also on
So
the uncertainty of
I'd have to raise my dark matter density by a factor of 4 or 5, I guess.
factor of 4 or 5 to compared to what?
If my rate if this cross section was really 3 times 10 to minus 26
Mhm,
rather than 6 times 10 to minus 25,
mhm. Uh-huh.
and I could make it consistent by raising the dark matter density you've assumed in your model by a
Mhm.
factor of 4 or something, 4 or 5.
Factor 4, factor 4. The cross section is factor
20.
more 20. Yes, factor 20.
But the overall signal is going as density squared, right?
Oh, yes, yes. So if in terms of density, so if there is a uncertainty of the dark matter density in the halo, so
Hmm.
if it changes a factor of 3 or 4, then if the gamma ray signal is proportional to the density squared, then yeah, it can be consistent with cross summary.
But does that raise any tension somewhere else? Do you, so why don't you favor such a solution?
I think yeah, I don't disfavor such a solution, but it's simply it is a bit it depends on the uncertainty of the Milky Way halo. So I'm not so expert about the dark matter modeling of our galactic halo, but
Hmm.
there are some many studies estimating the rotation curve and estimating dark matter density in the solar neighborhood. And the question is, okay, so factor of 3 or 4 change is then is accepted by some kind of observational study of the dark matter density profile of our galaxy. So my understanding is a factor of 3 or 4 is possible, but that's probably it's kind of close to the kind of maximum uncertainty
Hmm.
quoted by literature. So
Hmm.
maybe marginal.
Hmm. But
For
then,
example, if we change it 10 times in the density, maybe people agree, people make it get angry.
but then how do you explain the thermal relic? So you have to perhaps just to say a little bit about that.
Oh, okay, okay. But I mean, there's some possibility of
Yeah.
some theoretical possibility of that the difference from the deviation from the thermal relic is, of course, I'm not the expert again, but is so-called Sommerfeld effect is that is often quoted in the theoretical paper, but particle physicists argue that is some kind of Sommerfeld enhancement effect. If it is working, then annihilation can be enhanced compared with this kind of standard thermal relic. So I'm not so sure, but I'm not a particle physicist. But
Mm.
just looking at literature, I think there's some depending on the particle physics modeling. I think maybe so one order, maybe one or two orders of magnitude deviation from thermal relic is possible. That is my understanding.
Hmm. No, we'll have to look into it. Very good. We're at the hour now. So, if there are no further last questions, I think we should thank Tomo again for a very exciting result. And we heard it here first. So, thank you.
Thank you.